pass it over to Jim. He can do a self-introduction. Thanks, Jim.
Okay. Good afternoon, everybody. Thanks for having me. My name is Jim McDonald. I've been with Vic Gardner Instruments and Additives on the instrument side for about 27 years now, all in a sales capacity. If you're not familiar with our company, this is an older catalog. We no longer publish catalogs. We put everything online. But if you wanted to take a peek at this, you're welcome to. We've got a lot of different physical testing, attributes testing instruments, as well as all of our color and appearance testing instruments as well. We're going to talk about a few of them today. I brought in a couple if anybody wants to take a closer look at them. And I have business cards in case anybody wants to pick one up on the way out. And follow up with me on anything we cover today in this presentation. So I'll jump right in. Oh, I'm afraid it's not working.
Oh,
I need some technical assistance.
sometimes you just need to click into the screen
Okay.
because I added somebody on there and it listening to it.
Oh, very good.
Okay.
So when we talk about quality of a paint job, typically what we're talking about is uniform appearance. Uniformity of appearance in a paint job, whether it be in the marine industry, the aerospace industry, the automotive industry, it all has challenges. There's a lot of different things that can happen with the painting of a vehicle of any sort that create challenges that we need to overcome. There can be horizontally versus vertically painted parts. There can be assembled sections maybe that are off the vehicle and then assembled later onto the vehicle. There can be all sorts of varying environmental conditions, temperature and humidity when it comes to painting anything can lead to big differences in the overall appearance and then the perception of quality in the end customer. And so all of those things need to be taken care of. And finally, you've got different substrates and coating technologies typically come together on one type of a vehicle. And again, whether that be an ATV, an airplane, or a yacht. So ISO 11347 is the international standard that defines exterior surface appearance for the yacht industry. And this is a big document. It covers 12 different topics. It covers orange peel, covers color difference, gloss, fairness, sags, dirt retention, overspray, sanding marks, blistering, watermarks, polishing, blooming. There's a lot in this document for sure. I'm not going to cover everything that this document covers by any stretch. What I am going to concentrate on with you today are the three areas in which I'm most expert, which are orange peel, color, and gloss, and how they relate to ISO 11347 and how they relate to your industry. Jump right into orange peel. Appearance is influenced by the waviness that we see on a painted surface. We call it orange peel. Everybody knows orange peel. But there's another component to appearance that we as Vic Gardner put into the same category. It's an additional component to appearance called brilliance or DOI. Does anybody know what DOI stands for? Distinctness of reflected image quality. Or in layman's terms, how well can I see my smiling face in the reflection of the paint job, essentially? So we need to account for both of these if we're going to quantify appearance. So the visual perception, when we focus on the reflected image off that paint job, is the gloss. What's the specular component? And what's the brilliance? What's the mirror-like component that we see? And then when we focus our eye on the surface, it's almost like switching a switch in your brain. When you focus your eye on the surface itself, you're looking at the structures of the waves that you typically associate with orange peel. What happens is you need some specular component shining a light on a wavy painted surface. And then as you vary your direction and your acclimation of the painted surface, you get a varying amount of intensity of that reflected light back to your eye, leading to this perception of a wavy light and dark pattern. And that's what we associate visually as orange peel. It's important to note that appearance visually changes with observing distance. When we're 10 feet away from the surface, we can see that big blocking wavy type surface. when we're much closer, we can see the grittiness or the graininess sometimes in the painted surface. The other way to look at that is when we're up close, we can see the fine detail. And as we get further and further back from the paint job, essentially, then we're seeing more of a pattern, the larger pattern in the surface. So when it comes to the human eye and our perception, what can we see? When we're about 10 feet away from a boat hull or an airplane or an automobile, we can see surface structure of about 10 to 30 millimeters in structure size. And what I'm talking about is the top of one wave to the top of the next one. You think orange peel is a series of peaks, talking about the distance between those peaks. It's 10 feet away, we can see 10 to 30 millimeters in structure size. As we move closer to a foot or 2 feet away, we can see much smaller structure, 1 to 3, until we get to what's called the resolution of the human eye. Resolution of the human eye, we cannot discern the structure of under 0.1 millimeter in structure size, okay? We can't see it, but you're gonna find out that it's an important part of the next component after the wavelengths. So we need to measure it and consider it in our calculation. So the measurement procedure with our wave scan technology, and it's been around for years, in a variety of different instruments, including the marine industry, is that we replace the sun with a laser, we replace the eyeball with a detector, we put it all in a box, we put it on wheels, and you can scan it across the surface by some dedicated scan length and gather a bunch of information. And then you can see here as you scan across that wavy surface, just like with the human visual perception, you're getting a varying amount of intensity back to the sensor. And so it's going to give you different values. And it's going to send it through an optical profile. In the original wave scan scales that you would get are simply shortwave and long wave. And in the ISO method for your industry, it calls out measuring long wave. That's okay. But there's more to it than that if you're really going to dive into orange peel. So we'll discuss it in a little bit more detail. The relative dimension, the scaling itself is 0 to 100, 0 being mirror-like smoothness, and anything up from that having more and more waviness in that particular structure size. And now we've taken the long wave and the short wave, and we've since the 1990s, and since divided that out into more critical definitions, including a higher resolution shortwave and long wave expansion, so that we can really capture the entire visual perception of any painted surface out there. Okay, put numbers to that, quantify it so that we can engage, orange peel. So the classic scales again were shortwave and long wave. The new scales that include shortwave and long wave but are more definitive, called W, A, B, C, D, and E. And this is what we call the appearance spectrum. A lot of people are using this wave scan technology to make improvements to their appearance or to set boundaries or limits as to what the appearance should be. In the second part, remember, we talked also about waving, brilliance or contrast, sharpness, distinctness of reflected image quality. This is a very good contrast. This is a very poor contrast. It needs to be defined. DOI is a buzzword today in a lot of different industries, particularly in automotive, but I see it now in aerospace. I see it in anything that's painted and costs a lot of money. DOI is a new number that's being captured because people are concerned about how good is that reflected image quality of the surface. So you know it when you see it. What is DOI? If it's fuzzy and distorted looking, it's poor DOI. If it's sharp in contrast and more of a mirror-like image, it's very good DOI. So we talked about this 0.1 millimeter in structure size, structure that's too small for us to even discern. We can't make it out with our visual perception, but if you have it in your paint job, it causes a scattering of the light and a loss and a reduction in the contrast of the reflected image. A reduction in the contrast of the reflected image is a poor DOI. Furthermore, even the structure you can see in this WA and WB range, if you've got a lot of that, it causes a distortion in the outlines, contributing to that poor DOI. So in addition to the laser and the instrument's capabilities, we have a camera that essentially illuminates the surface, captures that scattering value, and gives you a final value that we call dullness. So dullness completes the entire structure spectrum, and people are now using this graphical information to pinpoint to really put a fingerprint on the overall appearance of whatever paint job that may be. They can then use that for process improvements. They can use that for, again, setting limits and controls and what's acceptable and what's not, tolerancing, all of those things. DOI is a function mostly of dullness. It also includes WA and WB. Just gives you its opposite from the 0 to 100 scale that I showed you for everything else. 100 is perfect DOI, perfect image forming quality, and anything down from that is less. And so here, because my dullness on the blue and WA and WB are lower than that of the red, I have a higher DOI, a higher number, and a better DOI. Okay. So again, a lot of industries, a lot of this industry included, are starting to use DOI in some instances to characterize what that appearance is. Just to give you a quick example, running through how people are using this appearance spectrum compared to your visual. You're not used to looking at numbers and graphs in comparison to what you're used to doing is looking at it visually. And so this is a good example to kind of show you how this works. If you've got a crummy looking surface that has poor DOI, floppy looking swell in the ocean type orange peel, it's going to measure bad. It's going to measure poorly everywhere, starting off high, getting even higher. This is a terrible graph representing a terrible paint job. I know if I want to put more paint on, I'm going to get better flow and leveling. It's going to smooth out. It's going to right inside of the graph. My appearance from a distance is going to appear smooth, but I still have all of this shortwave that's telegraphing through from a rough underlying surface. And so it's going to look gritty and grainy with poor DOI. I'm way out of balance. I'm shortwave dominant instead of in balance. And so that's a terrible looking appearance as well. I know that if I can do some surface prep to get less bleed through coming through, I'm going to get a much lower much lower shortwave, and it's going to bring back my contrast in the reflected image and improve my appearance quite a bit. But look here, remember, if I had a line across 0, it would be mirror-like smoothness, and it's paint. You're never going to get there. But here I just have a little bit of long wave, but because I don't have any short wave at all, I'm out of balance on the long wave side. And now that long wave pops out at me. So what people are trying to do in just about every industry that uses paint and makes an expensive type of vehicle are trying to get in balance, where they have a little bit of short wave masking the long wave, and I'm in balance and I have an overall good appearance. Okay. And if you can achieve this from part to part, from boat to boat, from airplane to airplane, got good harmony, and I think your customers are going to see. And so that's what people are doing with the structure spectrum in order to get a better handle on orange peel. And so you can see that by stepping through a couple of process parameters, and in your industry with your challenges, there might be a lot of different process parameters to achieve a better paint job and better appearance, but you can no longer just look at the visual and scratch your head and wonder what went wrong or what needs to be done. You can use this technology, this wave scan technology, numerical and graphical information to get a better finish. Okay. From Big Gardner's perspective, it's over since slide old, but we've had this technology in the different industries for about 35 years, starting with the old brick wave scan and now to the newest version, which is called the Wave Scan 3 Dual. And you can see, I can pass it around. You can see how it rolls on wheels. And what you do is just scan it across the surface to gather information, and all the data will pop up right on your screen. You can see these are some of the features of the new wave scan tool. We just came out with this a couple of years ago as the latest and greatest in the family. So you can store data and do a lot of things with it that you couldn't do with previous gen. So I'm going to keep moving in the essence of making good time and talk a little bit about color as well. our ISO method 11347 specifies a specific spectrophotometer to use for measurement in this industry. And that's a D8 specular included spectrophotometer. I know that's a lot of words and a lot of things that I'm not going to explain today. I give color courses that go an hour or an hour and a half or even 2 hours, where we dive into a lot of these topics. And today I've only got about a half an hour, I believe. So I'm going to try to burn through this pretty quickly. But ISO 11347 does recommend a specific type of spectrophotometer for color measurements so that you can quantify where your color falls in color space, and you can quantify what the color difference is from standard to sample, from paint chip to finished application, from original paint job to weathered paint job, all of these types of things. You can use a spectrophotometer of this type in order to quantify color, and this is the method. This is what's called out in the method for your industry. This, just to give you a brief, a really concise color course. In order to be able to do this, to be able to quantify color and to look at color difference, you need an instrument that will be able to quantify three things, the three building blocks of color. And one of them is an object, whatever that object is. In this case, it might be a boat hull. We need to quantify what that object is. We need to quantify the light source, the illumination that's going to allow us to see that object. And we need to quantify the observer. We need to actually quantify how people see and perceive color. And that's not so easy, but it's kind of an interesting topic. So we'll step through real quickly each one of them. When we talk about an illuminant, we know that white light, if you pass it through a prism, really consists of a whole mixture of many different colors. And those colors occupy a particular part of the electromagnetic spectrum from 400 to 700 nanometers. And the energy that comes off of these, that comes off of any light source or any object can be measured. Intensity, that energy that's coming out in different light sources can be measured, and at individual rate. And so in order to quantify the illuminant, I'm neglected to say, you can't see down under 400, that's UV, and then up above 700 is infrared, which we also can't see. But when we refer to color numerically, I don't know if anybody here has used a spectrophotometer or does any color science theory behind them, but when you do that, you're always referring to a number, a particular number on a color scale under a particular standardized illuminant. And the CIE Association has defined a number of different illuminants. They've measured the output and defined what those illuminants are. North Sky Daylight D65 is probably the most commonly used illuminant in the spectrophotometer, and would probably be representative of your product in 99.5% of cases, because it's representative of how you see a color outdoors in the sunlight. But then other industries have different challenges and want to use a defined illumination source of, say, incandescent if you're making kitchen cabinets or something of that nature, or fluorescent if you're making office furniture, that type of thing. But all of these things can be defined with the illumination. They can be measured. The output can be measured. It's important to note that, of course, objects look differently to us depending on the illumination. So if you have a red glasses case and you held it up outside, it might look quite differently to you than it would if you held it up under your bedside at the incandescent illumination. So numerically, color is always referred to as a particular number on a scale under a particular illuminant. Okay, so that's important. So the illumination can be defined. Let's define the observer. This is a little bit longer of a story, and I'm not going to get too much into it, but the Wright-Gild experiment goes back to the 1930s, and they redid it in, I think, 1964. And what they did is they put humans behind a screen with a slit in the screen that they could look through, and they could see a black partition, and they could see both sides of that partition. And then what they did was, shown on the one side of the partition a whole bunch of different colors, one at a time. And then the test subject had dials in the room that he was in, and could adjust the quantity of output from the red illumination, the green, and the blue to try to match that test color. And by doing this thousands of times with thousands of different individuals, color scientists and mathematicians were able to put numbers to how humans are able to mix and match colors to come up and standardized color values. So we've actually been able to standardize how humans see color. And again, there's more than that. And if you want to dive into color as a better course, we offer some free color courses all the time online. You're welcome to sign up for them at any time. Some of my competition also offers color courses, and there's a lot that you can find online as well. So finally, if we're going to be able to standardize on color and to complete the last building block, we need to be able to define the object itself. And so what happens with light in a painted surface is that light first strikes the surface and then rebounds at an equal but opposite direction. Most of that energy is lost as loss, but some of that energy then is reflected or selectively absorbed and then re-emitted by the pigmentation that's in the surface itself. Okay, and again, just like we can capture the energy that's coming out of different light sources, we can capture the intensity of the light at individual wavelengths to capture how much color is coming off the object itself. Okay. And that again is simplified. There's all sorts of other parts of this conversation that we won't talk about. But really, if you can define these three things, the three building blocks of color, the illumination, in the observer, and the object, then you can put that together into a color scale. And the color scientists over the years have put together a number of different color scales, but the most popularly used one, and one that is used in 90% of industrial color applications today of any variety, is the CIE LAB system. I'm not going to talk too much about that, but again, it's a three-dimensional way to place color in three-dimensional space on a graph. And once you do that, you can define the lightness, the L value, how light and dark it is, which is the L, the A value, which is how red it is or green it is, whether it's positive or negative, and the B value, which is how yellow it is, or negatively it's blue. Then you can define numerically where a color falls in color space. And then you can do all sorts of things with that. You can repaint the same color because you've got the values for formulation. You can do weathering studies, you can do degradation studies, you can do repair studies. Did my repair match my OEM paint job? All of these things. From an industrial standpoint, color science and color difference is used every day in thousands of different industries to see what's the difference in my color from this batch to this batch. Because again, all of these things are a perception of quality, and we need to harmonize them and make sure that they're controlled. Okay? So LAB is the system that's used once you define these three things. So again, color is part of the ISO method for your industry, there are 5 or 6 main companies that make spectrophotometers. I didn't bring a spectrophotometer, but the handheld spectrophotometers that will meet the needs of your industry to measure color. Okay? I recommend you look to Bic Gardner first. We make the best things. And the third topic that we're going to talk about that's listed on the ISO method is gloss. And gloss, the perception of gloss, again, requires a surface of some type. It requires illumination, and then it requires somebody to see it. And so here we've got the sun shining the light on the surface. That will, by physics, rebound at an equal but opposite direction and be detected by the observer. Okay. If that surface is a smooth, highly polished surface, then you're going to get a large amount of the reflection right to the detector or the human eye, and you're also going to get a very good, very precise reflected image. So good DOI with good contrast. If, on the other hand, it's a matte surface, or it's been roughened up, or for some reason it's textured or something of that nature, if it's not a smooth surface, something different happens. You get a lot of specular reflection off and out of the specular component here. You get some that's rebounding at an equal but opposite direction, but you're getting a lot that's lost. And so your gloss level is going down, and your DOI and your reflected image quality also is going down. Rougher the surface, the poorer the DOI, and the poorer the contrast and the reflected image. Gloss meter design mimics what you visually see gloss, and I'll pass this instrument around as well. This is a gloss meter we call the tri-gloss, and I'll show you why in just a second. But here we replace the specular sun with a light source, and we typically use LEDs for most of our instruments now. But then it's going to be shown down to the surface in a columnar fashion, but then it's going to bounce back in an equal but opposite direction and be captured on the other end by a detector of some sort. Same concept as how we visually see gloss. So what we're doing is we're measuring the total amount of the intensity of the light. Gloss is not measured and referred to as a percentage. A lot of people will make that mistake. They'll say, oh, it's 50% gloss or 72% gloss. How we refer to gloss. Gloss is referred to as a number of gloss units at a particular angle. Okay? A number of gloss units at a particular angle. It's important to note, especially in your industry, if you're using a gloss meter, checking gloss on a boat hull. Gloss is very dependent on curvature. It just makes sense, right? Because if the surface is flat, it's going to direct all of that energy correctly to the detector. But if it's not flat, if it's curved, then all of a sudden you're getting a much wider variation of how much specular component is getting away from the detector versus how much is actually hitting the detector. And so that's a challenge. If you're measuring gloss, always make sure that you're looking for the flattest portion of the product to measure. The defined angles of illumination from different governing bodies, and there's several more than just this, but these are the three most commonly used angles, 60 and 85. And the meter that you see there will measure all three. Some people want to measure all three angles of illumination, but you can see in every case, the specular component hits the surface and then rebounds at an equal but opposite direction where there's a detector there to capture that specular and put a value. Okay. Now, again, your ISO 11347 specifies 60-degree gloss angle, which is this top one. So from perpendicular, you're illuminating at 60 degrees, and then you're also detecting at 60 degrees. A 20-degree will look like this, an 85-degree will look like that. There's reasons why we would use different angles, but you only need to be concerned about the 60 because that's what your specification says to use. And by the way, that's also an angle that's specified in probably 80 to 90% of any industrial gloss specifications that I know of in hundreds of different industries. And so everybody uses a 60-degree gloss meter. Everybody's familiar with those values, but just don't forget the communication of gloss is done at number of gloss units at a particular angle. So it might be 46 gloss units at 60-degree angle measurement. And people often ask me why you have different gloss angles, and really the answer is because we see gloss differently depending on the smoothness of the surface. If I'm going to do an evaluation on a very shiny object, I'm going to put the light source almost directly over my head. That's where I see the gloss. That's where it shines into my eye. And so I want to be using a very steep angle meter to mimic how we visually see gloss. If I'm looking at a very low gloss surface like this plastic cover here, I'm going to put that specular component way over there, and I'm going to have a very shallow angle. That's how the light's going to shine into my eye. That's how I see the gloss, and that's how I'm going to see small gloss differences. And so this graph here sort of shows you with the explanation that these are 13 different contrived samples from very, very low gloss, 1, 2, 3, and getting more and more higher and higher gloss, all the way up to a very high gloss surface, 12 and 13. Well, if I'm evaluating low gloss samples, and again, low gloss, how do I visually see it? At a very shallow angle. If I want good gloss differentiation, if I want to be able to see the small gloss differences, I really should be using an 85-degree gloss. If instead I'm evaluating very high gloss surfaces, the 85-degree meter, it no longer sees that anymore. So it's a useless tool. And so I really want to be using a 20-degree that's going to see the small gloss differences in that area where I'm looking at the gloss, but then it can't see the low gloss. And so when it comes to most paints, they typically fall somewhere in the vast middle range. And that's why we see 60-degree gloss values as the specified value across most industries that use paint. Okay, so pretty good at the low end. It's pretty good at the high end. In that vast middle range, it's very good as well. Okay. So those are the three topics that the ISO method calls out, and Pitt Gardner happens to be the main manufacturer of all the instruments that meet these specifications. So we can help with any questions that you have, with any instrumental needs that you need, or if you have any instances where you need some help and would like somebody to come out and take a look at a boat or something, or a paint job with an instrument, we can do that globally. We have locations all around the world. And so that's just a general introduction of Pitt Gardner to you, of myself, and of the ISO method that is written and directed towards your industry specifically. Some of those other challenges, the dirt, the pinholes, all of those things, we do make some instrumentation that can help you along those lines as well. But those three topics, the first three, appearance, color, and gloss, are where we specialize and where we make very good instruments to help you tackle. And so I've left a little bit of time, I think, for questions, if you have any. Yeah.
How much do these instruments being passed around cost?
That's a tricky question. Is for a 60-degree gloss meter as low as about $2,500.
Okay.
And for a high-end all-purpose wave scan in the $30,000 range.
Wow.
Yeah, they're not inexpensive.
Yeah, pass that around.
It has four wheels, and so we price it like a car. Right? It is expensive technology. I do want to elaborate on that answer just a little bit, because we have seen an influx of cheap knockoff instruments coming into the US, particularly, that are of the same color, of the same design, of the exact same dimensions, but they're garbage inside, and they might be priced a lot more attractively. You will find very quickly that their best use is to toss into a dumpster. So don't be fooled by cheap electronic testing instrumentation. You'll never get what you pay for. Yeah.
When you're measuring that, the DOI, I guess, do you go in one direction and do the other direction?
It's a good question. And I always tell customers, because I'm asked that constantly, it depends. And so let's try it on your product, because sometimes the direction of application of paint will definitely affect both orange peel, more orange peel than it will DOI. DOI is typically more material related, but orange peel is typically more application related, flow and leveling related, gravity related. So some people have a specific direction that they're concerned about, and we'll set up their program to measure only in that direction. Some people want to get an average to see overall, is it good? And that's acceptable too, depends on what you're trying to accomplish.
And you're really colorblind.
Colorblind? Are you colorblind? I'm not colorblind, but I know color scientists that are colorblind. Color blindness affects about 2.5% of the male population, significantly less of the female population. There's all sorts of different color blindness. The common one is very simple red-green color blindness that affects men pretty frequently. But there are all sorts of genetic mutations that lead to different types of color blindness. And if you pulled up color blindness on Wikipedia, you could probably spend an hour or two reading about the different types. So, yeah. But it does. There are tests. We sell tests, and they're a good idea if you've got somebody in your organization that needs to be able to visually and accurately see small color differences. They should be tested. That person should be tested. And we sell these color blindness tests to companies all the time to determine who should be the best evaluator of color when it comes to the conflict or discussion.
One of the challenges with super yachts, certainly in Europe, is that not so much surveyors, but project managers would say to the owner, "Oh, your car's going to go just like your Bentley or your BMW or whatever," and it never does.
Yeah.
They can't get that 100% specification, and there's been a lot of work going on to try and say, "Hang on a minute, you can't promise that," and that's where the waveguide comes in. Because
Absolutely,
yeah.
we run into the same.
So it's managing expectations, isn't it?
Of course, and it's the same when a Mercedes driver pulls up to his Cessna and expects the same type of finish. There's so many different challenges that are involved in that. But this technology is used, like I said, globally in so many different industries to allow you to make those improvements, or at least help and improve and verify that those improvements have been made, or lead you down the process path of what do I need to do to make it better. Yeah. And so that's the value of this type of technology, I think.
I'm at the surface of solar cell.
Solar cells.
The surface of the solar cell.
We've done work with the surface on solar cells, but it's typically not. It's more color related, believe it or not. Multi-angle. I don't know of any applications with wave scan technology on solar cells, but if you think, glass. Windshield, certainly, and all sorts of film applications, plastic film and things of that nature. And then think of anybody that makes anything that costs a lot of money, whether it be, appliances to ATVs to airplanes and cars and boats. Everybody wants a good appearance. They want it to be harmonious, and constant improvements are afoot in all of those industries, and so this technology can help you in that area. It can also help verify if somebody says it's one thing. Well, now you've got a numerical comparison to say what it really is.
Yeah.
So,
of course, with a super yacht, appearance is king, isn't it? I mean, if you're spending 300 or 400 million,
yeah,
you want something that looks absolutely state of the art.
exactly.
Yeah, it's very important. The aesthetics of what it's all about, really.
That's right.
Yeah,
That's right. So I hope this was useful to you. If there aren't any other questions, I'll leave you to your day.
thank you very much. Don't forget to pick up your wave scout.
I can't leave that here, unfortunately.
It's gone. It's gone.
Wait.
Thank you very much. Thank you.
I'll leave my business cards.
Thank you very much.
You bet. Oh, thank you.